Sairam everyone. So in this session we'll discuss about different modes of operation, right? We already understood the current equation of transistor, right? And now we'll see different modes of operation. The popular three modes of operation in transistors are common base, common collector, and common emitter, right? So we'll see each one of them one by one, and then we'll draw their, or we'll see the variation of input and output characteristics. Okay. So first we'll start with the common base configuration. Common base configuration. Okay. So as the name suggests, it's a common base. So let me just quickly compare with the diode. So in diode we have just two terminals, right? Cathode and anode, P and N, right? So so there you can have only forward and reverse characteristics, right? And but in case of a transistor you have three terminals. So depending on your battery voltage in the two different junctions, that is base emitter and base collector junction, it can have multiple operation modes, right? We discussed earlier, like active mode, saturation mode, cutoff mode, and inverted mode of operation, right? So in the case of a common base configuration, so let me just draw a very simple schematic of common base configuration. So here is the transistor, and let me divide into three parts. So we have on the left we have the emitter and center base, and here collector, and we are considering this is an NPN transistor, and usually emitter is heavily doped, so I just put a N plus here. And as it is a common base configuration, so I just put the base terminal common in the input and output terminals. So in the input terminal, or in the input we have this base terminal and the emitter terminal, and in the collector we have, sorry, in the output we have collector and base, right? Now if you consider a active mode of biasing, so in the active mode the emitter base junction is forward biased, right? So we connect the negative terminal of the battery to the emitter, so N is getting negative terminal, and P, which is base, is getting positive. So this junction is forward bias, right? Emitter base junction forward bias, and base collector junction should be reverse biased in active mode, right? So N will be positive and base is negative, right? And if you draw the current flow direction in the active mode, so this will be our emitter current, and the collector current is also entering IC, and IV is in this direction or other way, right? Because IC plus IC plus IB gives us IE, so this direction is IB, and we can so the base terminal is common, so we can ground this terminal, is the common ground terminal, right, in this operation. Okay, and now let's define the input parameters. So in the input we have emitter and base junction, and in the input, if you see the input parameters, sometimes we just call it as IP, input parameters. So in the common base configuration, it is the current is emitter current, and the voltage is the voltage between emitter and the base, right? So how to write it? So base is in positive terminal, right? So base is at higher potential compared to the emitter, so we write base is in the front, and then we write VBE, right? So VB is the voltage, right? Input voltage. And what about the output parameters? So output parameters, we have in the current form we have IC, right? And the voltage is our this V. Okay, so this is VBE, and here the positive terminal is collector, so we write VCE, right? So VCE. So output parameters are IC and VC, right? Now when we plot the input characteristics, so input characteristics in the sense, I'll just write off input characteristics. So in the input characteristics, we vary input voltage and see the change in input current. Like in this case, we will vary the VBE, and we see the variation of IE when keeping some of the output parameter constant, right? So we can keep this VC as constant, and then we can vary the VB and see the change in input current, right? So let me just draw it. It will be much easier to understand now. Okay. So again, it's the IV characteristics. Oops. Okay. So in the input voltage, the x-axis we have VBE, and input current in the y-axis we have IE, right? Now in the output we have to fix some parameters. So let's fix VCE to begin with. VC is 0. So VCE is 0 means this voltage, right? The voltage between collector and base. So this voltage is 0 mean you can imagine that this collector terminal is kind of open, right? So we are not supplying any voltage in this. So this terminal is open. So this junction is not biased, right? Base collector junction is not biased. So in that case, the input terminal we have just VV, and we can see that emitter base junction, it is just a forward bias diode, right? So if you increase VV, the IE will increase as a forward bias diode, right? So it will increase exponentially, right? So it's a diode forward characteristics. So it has a V knee voltage, and then it increases exponentially, right? So this is for VCE equals to 0. Now if we bias the output junction or this collector base junction, so we put, let's say, some VC, some voltage. For example, let's say we are applying some 2 volts here, right? So this junction is reverse biased, right? 2 volts. So in that situation, what can happen? So when we increase, so it was just not biased, 0 to we increase the reverse potential, reverse bias voltage here. It could be 2 volt, 10 volts. So as we increase the reverse bias voltage, the depletion width in the base collector, right, this region. So this depletion width increases, right, as we increase the reverse bias voltage, right? So let's say the depletion width become this pattern, right? So and this junction is emitter base junction is forward bias, so depletion width will be almost negligible. I'm not drawing it, but what is happening here, if you see the base neutral base width, right, the effective base width, it is decreasing, right? As we increase the VCE, the reverse bias voltage in this, the effective base width is decreasing, right? So if the effective base width decreases, then what happens? Then in the base region, the carrier concentration will increase, right? Because we are injecting the electrons from emitter to the base, right? Now the base width is less, so the electrons will be crowded in the base, right? So the overall electron concentration gradient in the base, it will increase, right? So there is some effect in the emitter current, right? So So in that case, what happens is the emitter current will increase, right? Because there is a more concentration gradient in the base as the neutral base region is now narrower, right? So the curve, so again, it has this knee voltage, right? Like forward bias diode, but now the base width is less. So electron concentration gradient is more. So the emitter current will increase little bit more sharply, right? So let's say this is our VCE equals to 2 volts, and then if you increase further this VCE, let's say 10 volts or so, so this curve will become even steeper. Oops, the knee voltage won't change, so this may be VC is equals to 10 volts or so, right? So so this effect where this base width is changing as we increase this VC, so effective base width is changing or the base width is modulating, so this effect is called early effect, right? uh, Early effect. So early effect, early is a name of a scientist who discovered or who observed this phenomenon in a transistor. So with his name, this effect is known as early effect, or it is also known as base width modulation. So because of this early effect or the base width modulation, the emitter current is increasing a little more rapidly as we reverse bias, as we increase the reverse bias in the collector base junction, right? So this is our output, and yeah, we can always get this knee voltage, right? This is our VN, or sometimes we called it as threshold voltage, right? So this is just a forward characteristics of diode. We are changing the width of the base, right? So this is input characteristics. Now if you look into the output characteristics, okay, so in the output characteristics, what are the output parameters we have? So let me just draw. Yeah, so in the output we have the output voltage, which is VCE, and the output current is IC, right? So it is VCE versus IC, right? And we are changing the emitter current, right? So as we change the emitter current, different emitter current, we can see the variation of VC versus IC. So for one single curve, what we'll do is we'll keep the IE or this emitter current constant, and then see the variation of VCE and IC. Okay, so to start with, let's say our emitter current is 0, right? So emitter current is 0 in the sense kind of emitter terminal is open, and if you see this base collector junction, they are in reverse bias, right, in this configuration. So as we increase the VCE, so it will be like a diode reverse characteristics, right? So let me just draw it here. So the current flow will be the reverse saturation current, which is ICBO, right, which is almost constant, and if you apply some more of VCE, then the diode may break down, may happen, right? And this amount of current, when our IE is equals to 0, right? So this is just the reverse characteristics of the diode, and this current is known as the reverse saturation current, which is ICBO, right? Now, if we change the value of emitter current, then what will happen? If you change the emitter current, or if you increase, right, emitter current here, so in the transistor equation, if you see the current equation, that IC equals to alpha IE plus ICBO, right? So this we already derived it for a transistor, where alpha is the current gain, this current gain, right? And yeah, so in this configuration you can yeah, ICBO is our reverse saturation current, right? And this value of ICBO is very negligible if you compare with IE or IC, right? They're forward biased current, right? So it will be very less in active mode of operation. So and yeah, and the current gain alpha value is almost equals to 1, right? So in that case, the collector current is nearly equal to the emitter current, right? Alpha is nearly 1, and ICBO is reverse saturation current, which is very less, so you can neglect. So our IC, or the output current, is equal to almost emitter current, right? So as we increase the IE value, let's say now IE is usually the emitter current there in emitter current, the order is in milliamperes. So let's say 10 milliamperes. So the emitter current, sorry, the collector current, it directly almost equal to the emitter current. Now in this curve we are keeping the emitter current constant, so the collector current also will be constant, or it is independent of VCE. Collector current is only depend on the emitter current. Now in this curve, when you are doing this output characteristics, we are keeping the emitter current constant, right? 0. Now it is 10 milliampere. So where it cuts, right, this point, it is again the IC will be nearly 10 milliamperes, the emitter current value, right? So this is for again the emitter current of 10 milliamperes, right? And if you go reverse VC, right, if you change the polarity of VCE, or negative VC if apply, so it will be also forward biased. So in that case, this region goes to the saturation region. And then here, so I'm not drawing the cutoff region. So this beyond this line, I mean, every transistor has got a that is called breakdown voltage, not cutoff, breakdown voltage. So I'm not drawing beyond this breakdown voltage. If you apply enormous or very huge reverse bias in the base collector junction, right, this junction, so this junction will break down, and there will be huge collector current, right? So we are not crossing that limit. So let's say this curve is for IE equals to 20 milliamperes. So this cut also will be around 20 milliamperes. And okay, now in the output characteristics, we have a few regions, like in this region, right, where emitter current is 0, or or less than that, negative, like we are doing reverse bias in the input terminal, then this region is known as cutoff region, right? So below this I equals to 0, this region is called cutoff region, right? And when we reverse the VC voltage, so this region is known as saturation. This portion is our saturation region. And this portion, which is most important, is our active mode, right? Our active region. The transistor is in active region, right? So this is how the output characteristics of common base configuration. Now, if you move into common collector, so we'll just see for the common collector. Okay. So now the collector terminal. Okay, we'll start with the common emitter and then we'll come back to collector, because emitter and collector, common collector, they are very similar. We'll just start with the common emitter first. Common emitter mode. So in common emitter mode, the emitter terminal is common in input and output side, right? So I'll just draw it in this vertical way. So let's say this is our emitter, this is the base, and this is collector. So now here the emitter terminal is common. So I'll keep the input terminals on the left side. So base and emitter terminal, they are in the input side, and in the output we have collector and emitter. So emitter is common in input and output, right? Now for active mode of operation, so again we need to first define the transistor type. Let's say it is a NPN transistor, right? So emitter is heavily doped. So this terminal is positive forward biased, this junction, base emitter, and collector base junction will be reverse biased. Okay. The current direction, so this is our IB, this is IE, and this is IC. So this voltage is VBE, and this is VC. Okay, so collector is in higher potential, so VCE. Okay, now in the active mode of operation, so we drawn this figure in active mode of operation. So in the active mode, our base emitter junction is forward bias, and base collector junction is reverse bias, right? Okay, now let's define the input and output parameters. So the input parameters are, in this case, we have VBE, so voltage VBE, and the input
Sir, emitter collector junction is reverse bias. No?
Emitter collector junction.
Is reverse bias.
No, there is no junction between emitter and collector, right? They are in the two ends.
Yes.
Yeah, we have only two junctions, base collector base and base emitter.
Yes, sir.
Yeah. Mm. So in the input parameters, we have VBE. This is the input voltage, and input current is our IB. And in the output parameters, we have VCE, right? This output, this voltage, right? And the output current is this IC, right? Okay. Now let's understand first the input characteristics. Okay. So input characteristics, what we do, we vary the input voltage and see the input current variation by fixing by fixing the output parameters, like here VC, we fix it, and then we see the variation between these two, right? VBE and IB. So let's draw and see. So here we have VBE and the input current IB. Okay, and now we are changing VC, right? So to start with, if we put VC equal to 0, right? So VC equal to 0 in the sense this voltage is 0. So you can imagine again the our this terminal, collector terminal, is open, or you can sort it, doesn't matter, sort this two terminal. So as if this junction, base collector junction, this junction is I mean, it's not biased, right? So there is no effective potential between these two terminal. So this in this junction, right? So at that condition, if you see this base and emitter junction, so it is forward bias, so it will behave like a forward characteristics of diode, right? uh, yeah. So the voltage, and then it increases exponentially, typical diode characteristics, right? So this is for VC equals to 0. Now what happens if we increase this VC, right? If you increase the VC, then this N, right, this is the N type collector. So slowly this N type collector, or the collector side, will get more positive voltage than the base, right? So base is, now this voltage is kind of relative, right? Because we are not directly applying this VC between base and the collector, right? It's not directly we are applying in the between emitter and the collector. So the effective voltage between the base and collector will be depend on this also, VBE, right? So the effective voltage between the base collector junction will be subtraction, right? You have to subtract VBE and VC, right? Because here the base is, let's say, already 5 volts, and then if you apply, let's say, here plus 10 volts, then comparing base with the collector, the voltage will be 10 minus 5, or other way, if you take 5 minus 10, so it will be minus 5 volt, right? So this side both are in common ground, this emitter. So what is happening is, as we increase VCE, After some time, what is happening is this base collector junction will get reverse bias, and as we keep increasing the VC, the reverse potential between the base collector junction will keep increasing. And like earlier, we discussed the early effect, right? So this depletion width, as we increase the reverse bias potential, this will keep on increasing, right? Depletion will increase. So our effective base width or the neutral base region will reduce as we keep increasing VC, right? So let's say our VC is 10 volts, right? So in that case, now the base width has reduced. So what will happen to the base current? Base width is reduced, right? And now in this base region, there is a crowd, right? The electrons will be much more crowded, and when the electron crosses, or electrons are when the electrons are entering from emitter to base, right? So the probability of recombination will reduce because the base width is now lower, right? The base effective base area, or if you consider in 3 dimension, the volume is less now, right? Because depletion width has increased, so the effective base volume is less, so the recombination probability in the base will reduce. So what will happen? The effective base current will decrease, right? So the curve will be on this side, right? So base current will reduce, this is for VC 0, and this is for our VC equals to 10 volts, 0 volt. Okay, so in this, if you see for a constant VB, let's say this VB, maybe just 5 volts, just these are just numbers. So you can see the value of IB, it was earlier some values there IB, right? So it will be in microamperes, right? And now as we increase the VB 10 volts, so the effective or the value of IB here, it is reduced, right? It is decreased, and which is again the effect of early effect, right? Because of the early effect, right? So because of early effect, the base current, right, this IB decreases as the base width, I mean, it is called the effective base width, right? Effective base width decreases, and in turn what happens is, as effective base width decreases, the recombination probability decreases, recombination probability in the base, right? In the base it decreases, so the overall IV also reduces, right, as we increase VCE. And yes, as we VB increase, it's a forward bias diode characteristic, so that will follow, but effectively the curve will become more flatter, right, as we increase the VCE. So the IB will reduce. Okay, yeah. Now if you see the output characteristics,
Sairam sir.
Sairam.
Sir, for the common base, when sir we increase VC, IE sir increases. But sir here,
Yes, so mm, The concept is, okay, so let's just compare. Yeah, so in the case of a common base, right, we described it here. So they are kind of interrelated, right? This IC, IB, and they are related with which equation? This equation, right? So this is IC equal to alpha into IE plus ICVO, and in more general, the IE is equals to IC plus IB, right? Okay. So in the common base, the way we understood the early effect is as we are increasing this VCE, so this base width is increasing, right? Sorry, this depletion width is increasing, so the effective base width is decreasing. So there is more concentration. There is a more concentration gradient in this region, right? So the whatever the electron we are injecting into the base, for the electrons, they can easily get transported into the collector, right? So effectively the effectively the emitter current is increasing. So as they are interrelated, in this bias condition, what happens is our IC also increases, right? As we increase the VC, we are not keeping the IC constant here, right? So as we increase the VC, the IC will also increase, and effectively the emitter current increases because we have higher concentration gradient. And we are not monitoring here the base current, but if you see the base current here also, the base current will reduce, but we are not plotting it here, right? Because in our input parameter we have emitter current and base emitter voltage, but in the common emitter configuration we are plotting here the base current, right? So that's why the base current, if you plot even in the common base configuration, then you will see that IB is reducing. It will reduce. But we are seeing only the IE, right? Emitter current. So emitter current will increase because the the electrons which are injecting into the base, they can easily get it transported into the collector region, as this width is less. So the concentration gradient is more, and also the probability of recombination has reduced in the base, so obviously our emitter current will increase, and if you see the base current, it will decrease here also. But we are plotting in the common emitter, we are plotting the base current, so that's why it is reflected here, and we see that base current is reducing, right, in common emitter. I mean, the way of understanding is base current reducing because the base width is less now, so recombination probability will be less. So most of the electrons, they will easily transported to the collector side. So our base current will reduce. But if you plot emitter current here, then you will see that there is an increase in emitter current for sure here also. But our characteristic concept is like we take IB as input parameter. So we see the variation of IB, it will reduce. Don't confuse with IB and I. Yeah. Is it clear now?
Yes, sir. Sir, when sir BC is 0, then sir mm, base collector configuration becomes a reverse, sir.
Sorry, when VC is 0, then
Then sir base and collector sir become reverse bias, sir. Like there is VB, sir.
okay, so VC is 0. Okay, then the base collector junction will become
reverse, sir. Like if sir VC is 0 and let sir VB is 5 volt.
okay. Then the VB, I mean base collector junction will be reverse bias. You mean?
Yes, sir. 5 minus 0, then sir total is 5 volt applied in the base collector junction, sir.
Okay, let me just try to understand what you're telling. So this terminal we are putting 0 volt, right? I mean this battery is not connected, right?
Yes, sir.
So with respect to the base, now the collector voltage will be lower. So the base collector junction will be forward bias, right? Base is P, right? And P type is getting 5 volts and N type is getting 0 volts. So this terminal will be forward biased, right?
Yes, sir. Yes, sir. Yes, sir. Understood, sir.
Yeah. Okay, so this is our input characteristics. And now if you draw the output characteristics, so in the output, what do you have? Output parameters are VC and IC. Okay. So let's see the I'll just repeat this. Output parameters we have VCE and IC, right? Okay, so to understand this, I mean dependence between VC and IC, so let's just bring some few transistor equation which we derived earlier. We'll see mathematically a little bit and then we will conclude it. Okay, so we know the collector current IC is alpha naught IE plus ICBO, right? So in this case, this is common emitter, right? So this alpha naught is our common emitter. Current gain. Okay. And ICBU is the reverse saturation current. I'm not writing it off. Okay. And for a transistor, this IE is always IC plus IV. So I'll just replace this IE with IC plus IB plus ICBO. So which is equals to okay. So we are going to, we need this IC. So I'll take the IC on the left side. So IC into 1 minus, so this alpha 0 will go to this other side, right? So here we'll get alpha naught IB plus ICBO. This is IC. Okay. And now if you write down IC, so it will be alpha naught by 1 minus alpha naught into IB plus ICBO by 1 minus alpha naught. Right. So let's name this equation 1. Okay. Now we'll define, oops. Now we define one common emitter current gain. Okay, so this alpha 0 was, alpha 0 is is equal to alpha naught. So this is just simple current gain. This is the current current gain of the transistor, right? Current gain of the transistor, right? In any mode of operation, right? This is the common current gain.
So the current gain, if at all we know the current gain, then if you multiply with the IB, then we'll get IC. No, sir.
Yes. But this
Like,
is, sorry, yeah, go ahead.
sir, like alpha naught is considered as a current gain means then alpha naught of IE.
Mm-hmm.
We have in the previous one we have approximated it as alpha naught is equal to 1.
Mm-hmm.
So like here, you consider that way, then IC will be so many times much more bigger than IE.
Yeah, if you take alpha not near to 1, then
Then whatever we have as like IC is approximately equal to IE.
right,
But here, sir is telling current gain of the transistor means then it will go so high, no, sir.
which will go high.
Sir, IC.
Why it will go very high? Because alpha is nearly 1, right? So it will be near to IE, right? Close to IE. Oh, in this one, from here you are trying to conclude?
No, sir. Actually, I thought it is like if there is a current gain of the that HFE.
Okay.
So that one, there's values, the beta value considers. Sorry, sir.
Yeah, I think your doubt
Yes.
will be just cleared. Just wait for a minute. I got your confusion. Yeah. So just hold for a minute. Your confusion will be cleared. So common emitter current gain, let me define it once. So you're confusing with the beta. I got it. Common emitter current gain. So this is define it as beta 0, which is delta IC by delta IB. So right, it's like incremental change in the IC with respect to the incremental change in IB, right? So this is our output current, this is input current, right? IB. Okay, so this is nothing, just incremental change in IC with respect to incremental change in the IB, right? So this will give us a common emitter current gain, and from this equation 1, if you try to calculate this beta 0, this above equation, so beta 0 is delta IC by delta IB. So if you take a derivative of this, so in this you will get alpha naught by 1 minus alpha naught, and delta IB by delta IB, it will be 1, and this factor, it is constant, right? ICBO is reverse saturation current, and alpha 0 is transistor current gain, which is for a condition it is constant, right? So our alpha beta 0 will be, just take a derivative of this delta IC by delta IB, so it will be only alpha naught by 1 minus alpha naught, right? This term is constant with respect to IB, is constant, so the beta naught is alpha naught by 1 minus alpha naught, right? Considering ICBO is constant for a constant IB. Okay, and in this, so we can now replace this IC equal to beta into alpha IB plus ICBO by 1 minus alpha naught. So this 1 by 1 minus alpha naught, it is 1 plus beta naught. So let me just let's see that 1 plus beta naught if you do, so 1 plus alpha naught by 1 minus alpha naught, right? So it is 1 minus alpha naught, and if you just add it, you will get 1 only, right? Alpha naught will get cancelled. So with this equation 2 and 3, if you replace this equation 2 and 3 in equation 1, so we will get IC, the collector current. IC will be beta 0 into IB plus this is our 1 plus beta 0, so 1 plus beta 0 into ICBO, right? So this is one of the most important equation in this common emitter configuration. So this equation gives us the variation of the output current with respect to our input current, right? Now see the value of beta, right? So usually typically the value of alpha is nearly 1, right? So for example, a typical value if you take 0.98, if you take, then what will be the value of beta? So beta is alpha naught by 1 minus alpha naught. It will be 0.98 by 0.02. So it is about 49, right? Now if you take alpha naught, beta naught, right? So if you take alpha naught value near much closer to 1, let's say 0.998, then the beta naught, if you calculate, it will be this, so it will be 449, right? So you can see the beta 0, which is our common emitter current gain. Beta 0 is very sensitive to the alpha naught, right? So you can see that little change in the base current, we can see a huge change in collector current, right? Because the beta naught value can go as high as you can see that, right? Usually the beta value lies between 50 to 500, 50 or 40 to 500, in this range, right? So we can see that there is a huge current gain in this configuration, right? Now let's try to see the output characteristics. Okay, so we can extend this session bit because next session is free for you. Okay, so I'll just extend and complete this. Now we are trying to understand the output characteristics with these equations. Okay, so we are plotting basically VCE, output voltage, and output current is IC, right? Okay, so to start with, let's say our IB. So we are varying the IB here. Let's say the IB is 0. IB is 0. Let's go to the figure once. So IB is 0, mean we are not biasing this terminal. So this is just a reverse bias junction, right? This base and collector junction is reverse biased. As we increase this VCE, the reverse saturation current will flow. From this equation also you can see. Yeah. So in this IB is 0. So IC will be 1 plus beta 0 into ICBO, and this equation we can write it off like beta 0 IB plus ICEO, where this ICEO is the emitter reverse saturation current, common emitter reverse saturation current. So this is 1 plus beta 0 into ICBO. Okay, so only this ICO will flow, right? So it will be And if we apply more reverse bias, or if you increase this VC too much, then the junction may break and it can increase very drastically, right? So this current, the amount of IC will be at bit IB equals to 0. So this we are drawing for IB, base current 0. So this will be the emitter saturation current. So this is ICEO, common emitter reverse saturation current, right? So this is will be ICO. And now as we increase the value of IB or the base current, so how will this vary, right? So so we are now increasing IB, and you can see that it depends on this beta factor, right? And beta also depends on the alpha here, right? Yeah. So as you increase VCE, the beta value increases, and so there will be a large leakage current also, because this this ICBO, it is multiplied with beta, right? So if the beta increases, then ICBO or the leakage current will also increase, and as we increasing IB, so there is a increment factor which has much more contribution to the IC. So the curve nature will look like something like this. So I know this behavior, it's behaves in a straight line format. I'll just draw this straight line. Okay, so it's something like this. So this is for IB was 0. Now here IB, so yeah, IB order is microamperes, right? So you can write it as 10 microamps, for example. And this is maybe IB is 20, 30, maybe this one is 40 microamps. Okay, so in this you can see that the curve is not horizontal, right? It has a incremental slope also, because as we increase this VC value, even though the IV is constant, so what happens is the beta value increases. The beta value increases as we increase the VC. As we increase VC, the beta increases, and then what happens? Then yeah, so this contribution is increasing, and also the reverse saturation current, because now this ICBO is also multiplied by beta 0, right? So overall the collector current increases much more rapidly, right? So that's why the curve is like this, and if you extrapolate this curve into the negative x-axis, then you will see that this curve, all the curves, they meet at a particular point. And this voltage here, this is known as early voltage. And obviously this voltage is a negative VC, right? It will be this is the 0 and this will be negative voltage, right? And this voltage is known as, where all this extrapolated curve meets, this voltage is known as early voltage. And in this transistor, if you see the different bias, different mode regions, right? So here we have the saturation, cutoff mode, right? This region where the IV is less than 0. That means we are doing a reverse bias into the input terminals. So this is our cutoff region. And VCB voltage, VCB lies, VCB or input voltage is VCB only, right? Now input is VBE. And this is this direction is our VBE. And exactly if you see that, then this line this line defines that the VC equals to 0. And this region where the VC is also negative, right? This region is our saturation region. This is saturation region, and the rest, all this curve, this region is our active region, active mode of biasing. Okay. Yeah. So this is our common emitter mode of operation. And in case of common collector, if you try to draw it, so it's very similar to common emitter. We'll just draw the circuit, then you can easily understand that common common collector is very similar to common emitter. So just doing the same page so that we can compare. Common collector. So in case of common collector, the collector is common in both input and output, right? So let's draw the transistor. So this is our emitter now. This is base, this is the collector. And so base collector is in our input, and this is again an NPN transistor, similar. So here the input parameters. Input we have BC and VBC, and current is IB. Current is same IB, and in the output parameters we have VCE, right? This one VCE, and the output current we have IE. So you can see in this condition what happens is our emitter and collector terminals, they just got interchanged in the case of common common emitter, right? So common emitter and common collector, if you see, only the base emitter and collector terminal, they are just got reversed, right? And if you try to do the input and output characteristics of the same way, very similar way for the common collector configuration, so the input characteristics will be very similar to this one, right? Because in a transistor, the emitter and collector, the only what will change is the doping concentration between emitter and collector, right? So emitter usually it is heavily doped and collector comparatively lightly doped. So we'll see little variation in the in this IB, right? As now the collector is little lightly doped, so we'll have less number of carriers here, right? Unlike the emitter, so there will be some reduction in your base current, right, in the forward characteristics, but the curved nature will be very similar, so I'm not drawing it for the common collector configuration. And if you see the output characteristics now, the output where we define here this where is that beta 0 we define, right? Common emitter current gain. So in this case we'll have common collector current gain, right? So we'll just see that how does the common emitter current gain varies, and then we can conclude this configuration, right? So for common emitter, again the current equations we can write it off easily, IC plus IB, and then okay, so IC is alpha 0 IE plus ICBO, and then we can write it as, from here we can write IE equals to IC, so IC we can put it off this one, alpha naught IE plus ICBO. Now we need, for the output characteristics, we need the IE value, right? Emitter current. Earlier it was collector current, right? So IE into 1 minus alpha naught, it will be plus IB is there, right? So IC we are replacing with this, plus IB is there here. So again we are taking this IE to the left side, so IE into 1 minus alpha naught will be ICBO plus IB, right? Or if you see only the emitter current, so it will be 1 minus by alpha naught into ICBO plus 1 by 1 minus alpha naught into IB, right? Now we'll define the common emitter current gain, very similar to the common collector. So let's define common emitter current gain. So common emitter current gain is defined as gamma. So gamma is again change in the output current delta IE by change in the input current delta IB, right? So again from this equation, let's say it is A. So from equation A, what will be gamma value? So if you take a derivative with respect to IB, again this ICB is constant, and for a particular condition the alpha is constant, so this term will be full with respect to IB, this term is constant, so from the derivative this will be 0, and only from the second term we will get 1 minus alpha naught, and this is our common emitter current gain, right? So if you replace this gamma value on IE, you will get IE equals to gamma into ICEO plus IB, right? Now if you see the value of gamma, so how much it will be? Typical value of alpha, if you take around 0.98, then the gamma value will be 1 by 1 minus 0.02, right? So sorry, 50, right? So we'll get 50 here, and then the gamma value also you can see it will increase drastically, right, as this alpha value approaches towards 1, right? So here also we can see that we have a very good gain in the current, right? Little change in the IV, there is a huge change in the emitter current. And if you try to draw the this one the output characteristics in this case, so it will be very similar to this, right? Because the configuration is exactly similar, configuration is very similar to this, only we are exchanging the emitter and collector positions, right? So I'm not drawing it, you can draw it yourself, it will be very similar to this curve, right? So any doubts here? So with
No,
this yeah, so with this we are basically completing, or we know now all the 3 different configuration in transistors, and next session we will discuss a little bit about that which type of configuration we should use for different application, right? So sometime we need a voltage gain, sometime we need some current gain, sometime we need power gain. You might have already guessed it, right? Why do we need current gain? Obviously current gain we have in more current gain in our common emitter and common collector mode, right? And we'll discuss a little bit more detailed about it, like when you will have a power gain or a current or voltage gain in different configuration. So depending on our application we choose the different mode of operation, right? Okay, if no more doubts, we'll end this session here.